Hello everyone, my name is Steve Ulrich. I'm assistant professor in the Department of Mechanical and Aerospace Engineering at Carleton University, as well as being the founding director of the Spacecraft Robotics and Control Lab at the same university. So today's lecture is about spacecraft robotics, and this is meant to be a follow-up to the lecture titled Introduction to Spacecraft GNC, in the sense that now we're going to look at more advanced guidance, navigation, and control strategies, specifically to address a problem of enabling proximity operations with uncooperative target spacecraft. All right, so because we're proposing a new attitude controller, we're also interested into comparing its performance against what it's currently used on ISS. In terms of attitude control for the International Space Station, what they use is a PD controller given by this equation at the bottom of the slide. Here I gave the full PID controller, but in operations usually they don't use the integral component, so it turns out to be a very simple proportional derivative controller that uses the control moment gyroscopes on board the ISS to control its own attitude. So the way we validated the robustness of our novel attitude controller was by tuning it properly under nominal conditions that were defined by assuming that the target vehicle we're trying to capture was SpaceX Dragon vehicle. So we used its own mass properties and whatnot. And we also assumed under nominal conditions that the misalignments between the latching end effector and the grapple fixture on the Dragon vehicle were the nominal ones. So we're talking about 5 to 7 degrees misalignments about the roll pitch yaw axis. We also tuned the benchmark proportional derivative controller under those nominal conditions. And again, to validate the robustness to uncertainties in the mass properties of the target vehicle we're trying to capture, what we did was to increase the mass properties or the principal moments of inertia by a factor of 2. And we also assumed that now we're having very large misalignments between the two interfaces. We're talking here about 10 degrees. So that's very off nominal conditions. So what we did was to apply both controllers that were properly designed under the nominal conditions and apply them directly to the off nominal conditions and see how would they respond. See if they would deliver similar attitude regulation performance during the robotic capture maneuver. So these are the results we got for the benchmark proportional derivative controller under nominal conditions. And as you can see, the orientation and the angular velocity are both well stabilized within 3 to 4 minutes after the full rigidization between the two interfaces, so between the latching end effector and the grapple fixture. These are the nominal results achieved by the adaptive controller, and already you can see that there's a huge benefit of using our novel adaptive controller in the sense that we've been able to regulate both the orientation and the angular velocity of the International Space Station during a robotic capture maneuver down to 0 within, less than 2 minutes. So already there was an improvement over the benchmark existing proportional derivative controller. Next, what we did again was to apply the PD controller design under nominal conditions to give good results under nominal conditions, and then apply it blindly to those off nominal conditions and see how robust it was to the uncertainties and the mass properties of the target vehicle, and as well as to uncertainties or to perturbations inherent to the large misalignments between the two interfaces. What you can see is that stabilization time went from about 3 minutes to maybe 5 minutes, and even after 5 minutes you can still see residual oscillations in both the orientation as well as in the angular velocities of the station after the full rigidization between the two interfaces. Whereas with the proposed adaptive controller for the attitude of the International Space Station, you kind of see the same behavior as what's shown for the nominal conditions, implying that our adaptive control strategy is very robust to the uncertainties in the principal moments of inertia in a target vehicle. Or in other words, it means that our controller will be able to successfully regulate the orientation of the space station or any chaser vehicle that is robotically capturing an unknown target vehicle with some random principal moments of inertia. As shown in the graphs here, where you can see that we've been able to regulate both the orientation as well as the angular velocities of the chaser vehicle within the same amount of time, so within 2 minutes or so. All right, now that you've determined the full relative motion between the two vehicles using advanced computer vision techniques, that you've planned a way to bring the chaser spacecraft from point A to point B in close vicinity of the target or of the uncooperative target spacecraft, and now that you've been able to capture it, the next question is, how can you now control the motion of the chaser spacecraft now that its own mass has changed? So the problem statement here is that you have, again, a chaser spacecraft equipped with a robotic arm that goes and capture a non-cooperative target spacecraft or components of that target spacecraft, like a battery, solar arrays, a communication antenna, and all those added components onto the chaser spacecraft obviously change the mass of the chaser spacecraft, and it may disturb the relative motion performance. So say you have a chaser spacecraft that goes pick up a battery of a target spacecraft for on-orbit servicing purposes, then wants to undock and travel away from the target spacecraft, maybe do an inspection maneuver, for example. Well, the fact that you have an added mass to your own chaser spacecraft, it may lead to the problem that the relative motion won't be controlled as efficiently as it was when you knew exactly the mass of your chaser spacecraft. So the solution we propose here is very similar to the attitude control problem for robotic capture and maneuver, in the sense that we wanted to have this time a relative position controller which was robust to uncertainties in the servicer spacecraft mass in order to ensure very consistent and safe relative position control with minimal overshoots. I won't dive into the details on how we did it, but essentially it's the same idea. So we benchmarked our new adaptive relative position controller with standard proportional derivative controller. Both of these controllers were designed and tuned under nominal conditions when you knew exactly your own mass and there are no external perturbations affecting the relative motion. So the top two graphs are showing the nominal results for the benchmark controller for a scenario where you start in a docking configuration and then the chaser spacecraft illustrated in orange in those figures undock from the target spacecraft illustrated in blue, and then follows a circular inspection trajectory in the along track, cross track direction. And the bottom graphs are showing the same kind of results. So initially you're in a docking configuration, then you undock and do that circular motion around the uncooperative target spacecraft. So again, these are all results under nominal conditions, where the mass of the chaser is well known and when you don't have any external perturbations pulling and pushing you around. When you use the same controllers designed for nominal conditions and apply them to off-nominal conditions, defined now by changing the mass of the servicer spacecraft and by adding external perturbations, you clearly see that the top graphs that are showing the PD results are not as good anymore because the system's dynamics has changed drastically. The controller that was working fine for the nominal conditions does not work as good anymore unless you use the proposed adaptive controller, which is shown in the bottom two graphs. So if you compare these two graphs with the nominal results, you can clearly see that the results are pretty much exactly the same, implying again that our relative position controller, which is adaptive and hence changes its behavior in real time, is able to deliver consistent relative position tracking performance. Okay, so to summarize in this lecture, we went over some key guidance, navigation, and control technologies that are enabling autonomous proximity operations with unknown, uncooperative target objects. It might be an orbital debris, might be a depleted geostationary satellite, something like that. So first we looked at computer vision techniques that were meant to estimate the relative motion between a chaser spacecraft or a servicer spacecraft and that unknown target, relying first on a pair of stereo cameras. And that was tested through the Spheres Vertigo program at MIT on board the International Space Station. Then we looked at the same kind of solution, but this time using infrared camera, and that was done in partnership with Neptec Design Group. And this is what my lab at Caltech is currently working on. And once you've determined the full relative state vector between the two vehicles, then we looked at, okay, how can you plan a desired trajectory that will take you from point A to point B while avoiding any obstacles in the way. And that was done through a suboptimal guidance algorithm that was giving you a feasible solution as quickly as possible for operational constraints. You want to do things as quickly as possible. But if you have the luxury of spending a little bit more time on iterating on the desired trajectory, then you can reach a true optimal solution that will also minimize the path length. And then we looked at two capture strategies. The first one using a robotic arm, and we looked at how can we stabilize the orientation of a chaser vehicle during a capture maneuver. And that was done through a proposed adaptive attitude controller. And then we looked at how can we use a net kind of mechanism to capture tumbling uncooperative target object. And what we proposed is to use 4 sub-tether configuration. And by maintaining a constant tension in the tether, we've shown that we could effectively damp out the angular momentum of that spinning uncooperative target object about 2 axes. The only axis we are not able to control is the tether axis connecting the two vehicles. But we're working on different strategies to take care of the third axis. And finally, we looked at how can you precisely control the relative motion between two vehicles, despite the fact that the mass of the servicer spacecraft might have changed due to the fact that it might have picked up some components of the uncooperative target spacecraft. And that was done through an adaptive motion control system that was modifying its behavior in real time due to the fact that those mass properties information are unknown. Finally, I'd like to acknowledge the contributions from 2 of my graduate students in those projects. First off, Jianfeng Shi, one of my PhD students, who is working on the infrared camera computer vision, as well as Kirk Howell, who's currently working on the tether capture of a non-cooperative target object. And we're going to do some experimental results of that shortly in our lab at Caltech. Also, I'd like to acknowledge the technical contribution from Mr. Stéphane Ruel from Neptec Design Group in Canada, which is close to Ottawa. And that's our partner in the computer vision projects we're working on, as well as Andrew Allen from MDA Space Mission in Brampton, Ontario, with whom we worked on the robotic capture and maneuver of a non-cooperative target object, as well as on the path planning capabilities. Some of my former colleagues at MIT with whom I worked on the Spheres Vertigo project on ISS, so Alvar Sanz-Otero, who's head of the Space Systems Lab at MIT, Brent Tweddle, former PhD student at MIT, Greg Chemidov, the main developer of the path planning guidance law that I've talked about, who's also a NASA astronaut who performed the actual experiments inside the ISS, and Dihan Fourie, who's currently a PhD candidate at MIT as well. Also, I'd like to acknowledge the financial contributions from the Natural Sciences and Engineering Research Council of Canada in all those projects. Contribution from the Canadian Space Agency as well are gratefully acknowledged. And finally, the Ontario Centre of Excellence, who's funding the current partnership we have between Carleton University and NABTEC Design Group in the computer vision projects. So I hope you found this lecture interesting in that you've been able to learn a little bit more about advanced GNC technologies specifically designed to address a problem of uncooperative target spacecraft. Thank you very much.